Hello everyone. Um, Welcome to this week's lecture for the course Software Security. So in this lecture, we will be looking at like an introduction to GDB. Right. So GDB is basically a debugger. Right. So GDB is a debugger and it's part of the GNU suite. And so whenever we want to inspect the, so when a process is running and when we want to inspect its contents, as in the register content step by step, if we want to, if there is some error and we want to find out where the error is and which particular instruction, the low level details, right? So in that case, all GDB will be very helpful. And from a security perspective, um, GDB is really helpful in the sense you get to, so if you don't have the source code, right, and if you want to better understand the binary which is given to you with just those assembly instructions, you can look at the disassembly and try to understand. But running it through GDB would be helpful to better understand the logic, and it will aid you in finding out like how does the program or the binary react to some particular inputs and all those stuff, right? So this lecture, the main goal is to give a practical introduction to GDB and the basic commands so that to get you started. So these commands will come in handy in the later parts of the course when we do assignments in these software experts. And so before jumping into the lecture, a couple of things. Today I'll be releasing the first assignment, which is basically on disassembly. So it contains around 3 questions. That is one. And the second is I had mentioned that I'd be releasing some recorded lectures, but unfortunately, the audio part of that recording was not clearly captured. Instead of redoing the recording, I'm just doing it as a live session from now. So apologies for the confusion, and we are meeting after a long gap. So apologies for that also. I hope you sort of we sync up and we actively get involved in this course from now on, right? So let's get started with GDB. So basically we have, so let's take a dummy program. Say we have this main program. The main program, main.c is the C file, the source code, and its contents are pretty much very simple. We have three global variables. One is of integer, one is of int star, a pointer to integer. The other is a character, and the other is a array of characters, which is GLB underscore ARR, global array. And then we have two functions. One is fun1, and the other is the main function. And in the main function, we do some initializations. In the beginning, we declare some local variables A, B, and C, and then we also initialize the global variables to some value, and then we invoke fun1, and fun1 basically does malloc on the global pointer and initializes that pointer to that specific malloc to region in the heap, and then we initialize the array of integers in star array ARR, and then we print the contents of the array and just we return back. So just like a simple program. It does nothing significant, like a significant operation. Just declares a couple of arrays and the character and some local variables, initializes it, and prints the contents of some particular array. So this program we will be using and running it via GDB, and see what all we can do with GDB. How can we use this tool called GDB to better understand what this program is, right? So we'll compile this program. So I'm using the GCC compiler, and the flags I'm enabling -m32 and -static. Right, so -m32 is for the x86 32-bit ISA I want to compile it to, and hyphen static is for it should be statically linked library, right? Not dynamically linked. And that's it. And also I would like to enable the debugging flag. So basically when you now look at file a.out, which what the executable binary which was prepared, right, by the compiler, emitted by the compiler, you will notice that this specific keyword is inserted with debug info. Hmm. So if I don't include this hyphen g flag, and if you look at the type of the file emitted, you don't see this debug info with debug info keyword present in the type of the file, the type of the binary, right? So this hyphen g flag is usually to enable some debugging information, like extra information, which will be sort of embedded within the binary as part of the tear.out file itself. Right? So why don't, but usually whenever we release binaries, as in when it's the binaries are used in production, let's say you are a app developer and you are writing an application, you want to compile your application and give that binary to some client, to your clients, right? You won't be enabling this hyphen g flag and compiling your application. The reason being, when you include this debugging information as part of your binary, the file size of the binary will increase. So let's see what the file size of the binary is when we um, okay. Right. So if you notice this part over here, right, this denotes the file size usually, right? And right. So we'll use this command du. So du is basically disk utility, right? So if I compile using the hyphen g flag, and if I see the file size, so it's around 696 KB, and without the hyphen g flag it's the same. But so usually, like if we this, so this like an approximate size, right? So but if I use this ls hyphen l command, that's the file size, so this denotes the actual size over here, right? So this specific number and this number, if you notice, there are like change in some kilobytes or some bytes, right? So if you compile with hyphen g, it's more, actually the size of the file increases. So this is like a small application, this main.c, this logic. But if you take a like a huge, say your like your gaming application or something, if you enable this hyphen g flag, then lots of debugging information would be present as part of your binary. So what type of information is, it will record, it will track all your variable names, it will contain a copy of the actual source code itself, right? And it will try to map which lines of the source code map to which part of the assembly code, right? So all these things would be sort of present as part of the debugging information, so that when you try to look at the disassembly, it should be helpful. That's the main goal of the debugging flag hyphen g. So in that scenario, the size of the binary will increase a lot. And usually when you in production stages, you won't be enabling this hyphen g flag, and you will just be compiling it in a normal way. So now we have this. So for now, let us enable this hyphen g flag, debugging flag, and let's execute the program. So this is the output of the program. We are initializing a global array, and then we are just printing some local variables. Okay. So let us look at what GDB can do with it, right? So GDB is the tool as well as the command name, right? The command GDB, GNU debugger GDB. So to invoke GDB, you can either just do GDB, or you can specify the file name which you want to specifically invoke along GDB. So GDB dot slash a dot out, and over here if you notice there is a message specifying reading symbols from a dot out. So basically it's reading the ELF file and loading it into the memory and keeping it ready. So now if I want to execute this a dot out file within GDB, there is this command called run. So GDB is sort of like an interactive shell, but like an interactive terminal sort of setting, where it has some commands on its own which it will interpret in its own way, and using those commands you can interact with your executable binary and try to look at the internals of the binary when it's executing, right? So for example, there is this command called run. So run is basically it starts the program made out, executes it, and then exits it, and everything is sort of runs it within the GDB context, as in, so if you, instead of doing dot slash a dot out, which you do it via your terminal, instead of that we sort of open up GDB and load this a dot out binary, right? And then I key in this command called run within GDB, which GDB will understand. And when I execute it, it gets executed. But this is not much useful, right? This run command. So this is the same thing that we do outside GDB also basically. So what else can GDB offer? So an interesting thing which GDB offers, like the basic utility, is it sort of offers something called as breakpoints, right? So breakpoints are, for example, if you are going through some say you are executing this function, right? And before your invocation to call the fun1 function, I want to look at the memory contents of this global array at runtime. I want to look at where this GLB ARR global variable is being stored, where is this character array being stored, and what are its values being stored, right? So in those cases all, when I just execute the program, you won't be able to stop the program in between and look at the contents, right? Uh, Directly. But in GDB, you can sort of insert breakpoints. You can insert multiple breakpoints. So for example, I can insert a breakpoint over here, right? I can insert a breakpoint at line 23, at line 28, like that. I can insert multiple breakpoints, and whenever, so when once I execute the run command, when your program starts executing and it encounters a breakpoint, it stops executing over there. It pauses the execution, and it provides you to inspect the memory registers and all those things via GDB. So let us look at an example, right? So we have the main.c, that the binary loaded in GDB, and if I do run command, it executes. So now what I can do is uh, I can insert breakpoints, and the command to insert breakpoints is as follows. So break is the command, followed space, followed by the line number or the address at where I should insert the breakpoint, right? So if I know the name of the function, so for example, if I know like there's a function called fun1 or something, I can specify the name of the function, basically the symbol. So the symbol name or the function name I can specify, and I can do break fun1. And if you notice, it generates a message breakpoint 1 at this specific address, and file main.c line 7. So if you notice, file.main.c at line 7, I have declared my fun1 function, and the address at which it's present at runtime in the binary is this specific address, right? And GDB, what it does is, excuse me. So now what I do is when I start executing the program, you notice that it doesn't directly show this output. Instead, what it does is it starts executing and it pauses execution when it reaches fun1 at line 7, and it sees that it pauses execution, and you get control of the binary now temporarily. So you can interact with the binary and inspect its contents. So what do you mean by inspecting its contents, right? So what I can do is I can sort of look at what the register values are at the time when the call is being done, right? So if I do this command info followed by registers, right? So it shows the list of the registers. So since it's x86 32-bit ISA, it shows all the registers EAX, ECX, all these things, and other general purpose registers, and it shows the values that are present in each of these registers. And if you notice the instruction pointer, the instruction that is to be executed, right? It's specified as 0x8049CE5, and if you notice it's mentioned over here breakpoint 1 at this specific address 8049CE5. So when this instruction pointer, the instruction which is being executed is the specific one 8049CE5, it pauses execution since I have registered a breakpoint at that specific instruction before the program gets executed using this break command. It pauses execution. So now what I can do is now I can sort of okay. So now what I can do is list. So there is this list command which shows your source code if it's present. Okay, and uh, and the other command. Right, and so if so this is one command, list command, and say if I want to um, look at my stack contents, right? So like this is the starting of fun1 which I have put breakpoint. So if I look at the disassembly, so let me generate the disassembly of the file, right? So if I generate the disassembly, so this disassembly fun1, and if you notice this is starting of the function, it's present at this address, and this is where I have paused execution. Say if I want to look at uh, look at the insert a breakpoint at this specific instruction, right? So which is push EBX. So what I can do is I can just open up GDB and key in the command break 0x hexadecimal. So this is so this basically I should do it as break star 0x. So star is because I'm actually referring to a memory location, right? So star is star address, right? So either it can be like break fun1 like the symbol name, or it can be break star followed by the address in hexadecimal notation, 0x something like that. Okay, so now I have registered a breakpoint, and so currently I have actually I'm present at this specific EIP. So if I just write info register EIP, so this it shows the value of the EIP register, and now what I can do is the execution is paused at this specific instruction 8049CE5, and I want to continue execution, right? And when I continue execution, it will stop at the next breakpoint, whatever comes first, whatever is being registered, it stops at that specific breakpoint. So for that, there is this command in GDB called continue. So it continues execution until the next breakpoint. So I do continue and it breaks at this specific instruction address which I have specified 8049 CEC between function 1, fun 1, and this is breakpoint 2. And now if I look at info register EIP, whatever the value of that instruction pointer is, right, it shows that the value of EIP is 8049 CEC. That's exactly where I had inserted the breakpoint. And if I look at the info of all the registers, right, so if I look at the code, right, before this instruction 49 CEC, you had two other instructions. We had a push instruction, and then we moved the value of ESP into EBP. So basically, say if I had ESP value of so at previously the value of ESP was 0xFFC0DC over here, or to make it clear, let us see the value of EBP, right? That will be clear. So ESP was FFF, so EBP was this specific value when I had paused execution at this specific instruction 8049 CE5, right? And now when I paused execution at 8049 CEC, my EBP value should have been changed. So now if I notice the EBP value, it's changed to C0D8. So initially it was C108, now it is C0D8. Okay, and it is actually move EBP comma ESP. So the contents of the ESP register is copied into EBP register. So what was the content of ESP register in the first place? Where at the first breakpoint, if we notice, it's C0DC, right? But we did a push operation in between, so it gets incremented by 4. So sorry, it gets decremented by 4. So basically when the stack grows downwards, right? So if I push something into the stack, it subtracts 4 bytes, and the ESP gets subtracted by 4 bytes. Stack pointer gets subtracted by 4 bytes, right? Subtracted by 4. So from C0DC it gets subtracted to C0D8, and that value is copied into the EBP register. So when I pause execution at this specific instruction, my EBP value has been updated to this specific value. So that's what you can see when you look at info registers at breakpoint 1. Your EBP is pointing to the older value, right? And when we look at the EBP value at breakpoint 2, it's been updated, right? So like this, you can sort of pause execution in between and look at the register contents. That is one. The second thing is, if I want to look at what my memory contents are. So for example, there is this command called print, right? The print command. And print, basically what it does is you can print any specific address or any specific variable. So say for example, I know there is this variable called glb underscore array, right? So what I can do is I can print the this variable glb array, and since we have access to the source code and the debugging information is present because the -g flag is enabled, it knows that it's accessing a character array, and it prints element of 10 elements in that array, right? It prints all the values. And if you notice, right, if you notice the contents of the array, it is A and B, right? The first two elements, and others are all null bytes. So if you notice main.c, before I invoke fun1, I initialize the first two elements of glb underscore arr to A and B, right? But if I want to look at some arbitrary memory address, right, how should we look at that? So for example, I want to look at GLB underscore ARR value, but sort of in another way, right? So what I can do is I can find the address of this variable wherever this array is being stored. I can find the address. So how do I find? I just use the ampersand sign, similar to how you do it in C code, the address of operator. The same way I use this ampersand sign address of operator, and it gives the address where this GLB underscore array is being stored, right? And this the address. So now there is another command called the x command. So x is basically memory dump, right? Dumps the memory contents. It does not sort of know the semantic value or something. It doesn't know whether it's an array or a single integer or a structure or something. Instead, what it does is it just dumps the array, dumps the memory contents at that specific address. So there is a format for this command x. So basically x slash followed by that, what we do is we should first specify the number of elements that I want to print out, right? And the notation I want to print out the elements, whether in hexadecimal or as a string or as a byte or as a octal or as a decimal number. I should print out the elements. I should or as a binary, right? I should output the elements, and then the size of each element, whether it's like 32 bits I should interpret, or as 4 or as 8 bits, or 1 byte or 2 bytes or 3 bytes. It depends, right? Size. So this the notation, this the format of this x command, and followed by this I should specify the address where from where I should dump the memory contents, right? So this the um, format of this x command. So let us see an example. So I'll be giving this. I have this command x slash 32xw and followed by this the address. So let us look at each part of this, right? So we have specified the address as the starting of this GLB ARR array, and if you notice 32xw, it's basically 32 denotes the number of elements that I want to output. X denotes whether I want to denote it as a hexadecimal form or decimal or binary form, right? And W denotes the size of each element. It's so W is word size, which is 4 bytes, 32 bits. Sorry, not yeah, 32 bits, right? So if you notice over here, um, each row so each element is of size 32 bits, that is 4 bytes. So that corresponds to this W keyword, key character in this command. And X specifies the hexadecimal notation, right? So if you notice, all the elements that are dumped by this command, the memory contents, is sort of present in hexadecimal notation, and the number of elements that get dumped is actually 32 elements, right? If you notice over here, each row is sort of as 4 elements, and you have 8 such rows, right? So 8 into 4, 32 elements it's being shown. So how do we interpret this memory dump, right? Um, so the way to interpret this memory dump is the left hand side, this blue colored column is basically the address, right? And the address and the corresponding value or the data which is being stored at the address shown in this left column. Right. So yeah. So this the way we should interpret the results. So for example, I specified the address wherever this global array is being stored, right? I found out the address using this print command, print slash x, right, underscore glb array, ampersand glb array, and then I do the memory dump present at that address. So when we uh, look at, say for example, the first row, if you notice at present at this address 80E6C8C is this global array, and the first 4 bytes has this value, and the second 4 bytes, right? So the second 4 bytes means 80E6C8C plus 4, so that's basically 8, so 90, right? So at 6C90 this value is present. It occupies 4 bytes. 6C94 this specific value is present. 6C98 this specific value is present. So it sort of contains the values for totally it contains each row, it sort of contains 32 what 32 bits, like 4 bytes, right? So each address is like contains stores 1 byte of data, right? So 8C and then up till 6C 8C up till 6C 9B, right? You have all these values being stored. 4 into 4, 16 bytes of data being stored, and the second row starts from this specific address 6C 9C. So like that, if you notice, um, overall all the contents present at all these memory locations starting from 6C 8C, each at 4 bytes location, right? You sort of get 4 bytes of data from starting from this address 6C 8C, and you interpret the data. So all the data which is present in your memory is binary, right? Zeros and ones. It's up to the interpreter, up to the user or the binary to interpret that data. So for example, if I want to interpret that as a character, so character is in the ASCII notation. For example, small a, lowercase a is the character is 0x61, the hexadecimal notation, ASCII notation for lowercase a. And but the same, if I want to interpret it as an integer, it's 0x61. So both ways you can interpret either as a character or an integer, right? Or like a normal hexadecimal form. So here I specify it that it has to be interpreted as like raw 4 byte data starting from this address. So from this address onwards, 8C onwards, it interprets all this data as 4 byte chunks, and outputs that data in this format, size 4 bytes, and similarly it outputs 32 elements in hexadecimal notation, right? And if you notice over here, um, global array, the address starts from the 6C 8C, and if you notice, we have actually initialized the first two elements to characters A and B. So here if you notice, these are the first two elements of the global array. So this is the first 4 bytes in a global array, and if you notice, the lower significant bits, right, the bytes, is denoted by 62 and 61. So that's basically 61 is represents the ASCII notation of lowercase a, and 62 is the ASCII notation of lowercase b. So for example, if I just do this man ASCII command, and it shows the ASCII table, right, for all the alphabets and all those things. So for lowercase a, if you see, this the hex column and the character column. So for lowercase a it's 61 and lowercase b it's 62. So if you notice, right, this is the value that we have specified in the initialized as the first two elements of the array, and also x86 follows this little Indian notation, where the lower significant bits sort of get stored in the lower address, right? So that's why A gets stored in the lower address. The first element gets stored in the lower address, right? and the second element gets stored at the next address like that. So basically how we should sort of interpret this is at 6C8C address 0x61 is stored at 6C. So the better way to look at this is if I, instead of giving word size, say if I give it as byte size. So now it will be clear, right? So at 6C8C address I have this value stored 61. At 6C8D address I have this value stored. At 6C8E it's null byte, and similarly 6C8F it's null byte, 6C90 null byte, 6C91 null byte, 6C92 null byte, 6C93 null byte, 6C94 null byte, right? So how am I able to get this output? So instead of giving it as, to interpret it as the memory dump in size of 4 byte chunks, I just wanted to interpret it as 1 byte chunks. So now it separates each value, each byte on its own, and it specifies in each row like sort of 8 bytes, right? And we have 4 rows like that. Okay, so instead of a byte, so if I want to interpret that as a decimal or something, I can specify it as a D, right? So if you notice, we, instead of getting 0x61 I get it as 97. Now instead of a decimal I can represent it as a string. So now if you notice, um, so now if you notice, starting at this address 6C8C, instead of showing it as in hexadecimal notation 61 or 62, it shows it in the string notation, which is AB, which we had initialized in the program as it is, right? A and B characters. So it shows it in the same format. Okay, A and B, and the others are all sort of null bytes. So this is what the memory dump usually does. You have this X command, and you can specify X slash 32 xs. So X slash, so this over here X slash 32 is the number of elements in which format and the size of each element, right? So based on this your memory dump will show. So if I sort of do the same command X slash 32W, and if I just press enter over here, the cool thing is you don't have to change the address each time. You can just keep on pressing enter, and what it does is it will just repeat the same command, but it will just keep on incrementing your address and it will show the entire memory dump. So if I just keep on clicking enter, it will just keep on dumping memory in whatever format that you are given um, in the latest command, right? In word size hexadecimal notation. So this is the memory dump command, and we looked at the contents of this GLB array. So now instead of, you know, this variable name and you are looking at the contents of GLB array, but say if I want to look at the stack frame, or if I want to look at some specific um some random address, right? So for example, I can use this command info register esp comma ebp. So it shows info register esp and ebp. It shows the values of the stack pointer and the base pointer registers. Now what I can do is I can specify what the um, so I can show like this, right? Info register ESP, EBP, EBX. So these three registers I'm looking at currently, and if I want to uh, okay, this is not the command. One second. So, /x. Okay. So now so okay, I am looking at these registers ESP, EBP, EBX. Okay, and wait. So I'm looking at these four registers: the ESP, the base pointer, EBX, and the current instruction wherever it's currently paused execution, right? At the instruction pointer CEC, 9 CEC. So 9 CEC is basically this specific instruction. So I have not yet executed this instruction, push EBX, okay, and it's sort of paused at this instruction. It has not yet started executing this specific instruction CEC. It has paused execution before executing this specific instruction. So now what I want to do is I will want to inspect the contents of the stack. So how do I inspect the contents of the stack? I can just do the same command x/32xw, print 32 elements, each of 4 byte size in hexadecimal notation. But instead of specifying some global array address or something, what I can do is I can just specify $ESP and it will show. So if you notice, what it will show is it will take the value present in this stack pointer as the address from where it should dump the memory contents. So if you notice, ESP has this value FFFFC0D8, and starting from that value itself, it will dump all the contents, whatever is being stored at that from that location, right? And so what I can do is I can minus sort of 8 bytes and show, right? So I can sort of minus 8 bytes and show. So instead of starting from C0D8, I sort of started from C0D0, okay? And I look at the stack contents over here, right? So these are the stack contents. So if you look at, so when your program is executing the binary, a.out binary, and at this specific location before executing this instruction, if you pause execution and look at the stack contents, this will be your stack contents, right? And if I just press enter, it will keep on continuing. Okay. So now what I want to do is I want to see where this, how this instruction executes, this push instruction, right? So I know that these are my register values, okay, and I know the contents of my stack also. So these are the contents of my stack. Now I want to just execute this single instruction, right? And I want to step through this instruction and see how this instruction executes. So for that, what should I do? I should again insert a breakpoint at this location and all that stuff. But instead of doing that, what we can do is, there is a command called step instruction, step instruction, right? So this is a command, and the short form of this command, the abbreviation is SI, step instruction, single step, right? So SI is a command, and if I just do SI, right, so what it does is, so it sort of single steps through the instruction. So now if I look at the register's value, the EIP is now incremented. It now is pointing to instruction CED. So basically it means it has not yet executed CED. It has executed this instruction CEC, and it has paused execution, right? I just executed one single instruction. I've stepped through this instruction and it has paused. And if you notice, my EBX value remains the same, but my ESP value has changed. So comparing to the previous value, initially it was C0D8, but now it's C0D4 because I have pushed the EBX register, and by pushing it, basically you decrement the stack pointer, right? Pushing is decrementing the stack pointer because your stack grows downwards in x86 uh, ABI format. So your stack pointer is decremented by 4 bytes. So why 4 bytes is because your that's the data being stored, right? Because EBX is of 4 bytes and that value is being stored. So how do I know whether it's being stored successfully or not? Let us look at the memory contents of this stack. So I'll use the same ESP command, but instead I'll just use 0x4. So right, so if you notice, it starts from C0 D0, both these outputs. So this output is before the push instruction, and this is after I single step through that specific push instruction. So if you notice this second element over here, before it was some element, some value present at the location C0 D4, which is having some value FFFF C1 D4. But after I single stepped through the instruction, the push EBX instruction, it has this value at C0D4 address, right? It has this value 80E5000, which is nothing but the value of EBX register. And the ESP register, which is pointing to the top of the stack, has this value. So actually I am printing ESP minus 0x4. So 4 bytes minus ESP, from there I am printing all the memory content. So basically my stack pointer is pointing to this specific location, and that location has this value, which is actually the value of the EBX register, which is being pushed onto the stack. So this is how my stack contents are being changed whenever I do a push instruction or a pop instruction, right? And you can notice that my ESP register is updated, and the stack content is also updated. Okay, and how I did this is I used this SI command, which is step through a single instruction command. It basically steps through each execution, each instruction. So if I again like step through, use this SI command, you will be executing this instruction sub ESP 0x14. So basically sub ESP 0x14 means x slash 32. So if I look at the contents of the register, right, initially my ESP before the sub instruction, it was C0 D4, but now if you notice, it's sort of, I have subtracted the 0x14, so it's now C0 C0, right? So like that you can keep on stepping through the instruction, and you can look at the memory contents using the dump the memory dump, or you can look at the register contents and all those stuff. So this is basically the set of commands that you would be using in GDB, right? At least the basic commands. So now let's just step through another instruction, right? So now I want to execute this instruction. So it's currently at this paused at this instruction 49CF0, which is basically this instruction, the call instruction. So the call instruction basically it calls some location. It calls some function which is present at this location 8049BC0. Right, so if I just single step through this instruction, if I look at the contents, right, so if you notice the EIP value has changed, right? So that is one. So this is how you use GDB usually, right? We looked at some commands, right? We looked at the run command, we looked at the continue command, right? So say I pause at a breakpoint, and now I just want to continue until the next breakpoint. You use this command called continue, and then I'm paused at a breakpoint, but I want to sort of step through single instructions starting from that breakpoint, and look at the memory contents, the stack contents, all those things. You use this command called SI, and say now I want to finish execution of that particular function. So currently I am within this function fun1. I want to finish executing fun1 function and just return back to whatever whatever function called this function fun1, right? So basically I just want to get through that end of that function's execution. So there is this command called finish. So basically it finishes the execution of that currently executing function, and stops over there, pauses execution over there. So now if you notice the registers, so if it notices the EIP value, the instruction pointer is this specific value 49CF5. So 49 CFI, if you notice, um, right. So 49 DF7. So I just executed the finish command again. So if you notice, it's actually pointing to this specific location over here, right? So it has paused at this instruction pointer 49DF7. So it is basically, if you notice the previous instruction, it was the call to function one, call fun1. So this over here, right? And this the call to fun1, and when it returns back to main function, that's where your fun1 finishes execution, right? So when I execute this finish command, I have not inserted any breakpoint, but it, when I use this finish command, it pauses execution after finishing, stepping through all the instructions present in the remaining instructions present in that fun1 function, and when it returns back to the main function or whatever function which called this fun1 function, it pauses execution over that. So that's why if you notice, it has paused execution before at this specific instruction, right? 49DF7. And if you notice, it specific outputs a value, like a statement over here, value returned is 24. So how does this know what the value of the um, program is? Like, I'm not returning any value actually from fun1, but still it mentions it's returning some value. So if you notice that what my contents of the EAX register is, so according to the x86 ABI, all your parameters, whatever you pass it to your function, is pushed onto the stack, whereas when you return from a function, the return value is populated in this register EAX, and it is returned back to your the caller function, so to the main function, right? So if you notice that the register EAX, it is having this value 0x18, which is in the decimal form 24. So looking at this register only, it specifies that the value returned by fun1 is 24. But actually we are not using the return value in any place, and it sort of, it's like an inbuilt property of this GDB to just, whenever I'm using this finish command, since I'm exiting that function, it wants to give like a semantic meaning, right? Some output, so it specifies that whatever is present in that EAX register, it treats it as the return value and specifies. Okay, so this is the finish command. So now I just want to continue execution, right? So I can just do continue, and now if you notice, it just exits the process, because after I execute this fun1, and after this I have not inserted any breakpoints in the remaining part of execution. I had inserted one at fun1 beginning and the other at the there's like 5 instructions in the starting of this fun1 function. And when I just continue execution, since there are no more breakpoints, it resumes execution and it just exits normally. Okay, so this is the use of GDB. So we, what all commands, if we looked at, if we just see, we looked at the print command, we looked at the continue command, we looked at the run command, we looked at the command single step through instruction, we looked at the finish command, and we looked at this command called x, which follows some particular format, right? And then we looked at info registers, right? And you can specify any register name, or you can just display all the registers like that. And there is another command also. So the same info command, but you can, there is multiple options over here. So for example, the same info command, what you can do is, there are multiple options, right? So what we had used is, we had used info registers, right? So that comes over here, the info registers, list of integer registers and their contents for that selected stack frame, right? Like at that point of execution. But say if I want to um, uh, get info about all the breakpoints which I've inserted. So for example, I can do it info breakpoints. So it will mention that I have inserted two breakpoints. The address where that breakpoint is present, and also if the debugging information is present, it will specify the line number and all those things, the function name and all those, and it will also mention number of times that breakpoint has been. So say if I'm executing the call to fun1 within a loop, right? Then in that case I'll be hitting this breakpoint 1 at start of fun1 multiple times, right? So it shows the number of times I reach this breakpoint. Okay, and this is one. So now if I want to so there is this another info you can try to use this info locals, right? So for example, I can do so break. Say I'm just putting a breakpoint at some arbitrary location, right, within the main function. After I finish the call to fun1, I'm inserting a breakpoint. So I do this. Okay, so it should be 0x since it's hexadecimal. So break star 0x. So now if I do see, the program is not being run, so you should start running your program, and now it's at breakpoint 1, which I'm not interested in. So if I look at info breakpoints, there are actually three breakpoints now. So one, the first two within the function 1, and the third one is in the main function, and I'm interested in this the third breakpoint and not in the first two. So what I do is I sort of quit from the process now, and what I can do is I can disable breakpoint 1. So now if I do info breakpoint, if you notice under this column enabled or not, breakpoint 1 it's mentioned n, which is not it's disabled, right? And I can also disable breakpoint 2, which I'm not interested in currently. And now if I do info breakpoints, the first two breakpoints are sort of disabled. Now if I run the program, right, if you notice it has skipped breakpoint 1 and 2 because they are disabled, and at breakpoint 3 it stops execution. Breakpoint 3 is within the main function, and now if I can use this command called info locals, and info locals is basically it mentions what all variables I'm being using, the variable name and their values, all the local variable names. So A, B and C are the local variable names which I'm using in main function. Okay, but usually this command won't be that helpful in production scenarios or in your assignments, because if I exit from GDB, and what I'll do is I'll remove this -g flag, and I execute the same, recompile the program, and I get the a.out without the debugging information, right? Since the -g flag is not present. And now what I do is I will execute within GDB, and I do the same breakpoint. So B is the acronym for break. Okay, so instead of doing break, you can just specify it as B. Okay, and it's the same way for so I just insert a breakpoint B star, the same address. Okay, this within the function main, right? Fun1, after the call to fun1, it is within the function main. Now I run the program. So instead of doing run, I just specify it as R. So I run the program and hits this breakpoint 8049D F8. Okay. Now if I do the same info locals command, it doesn't specify the local variables present in the main function. The reason being, when the -g flag is enabled, it has a symbol table and all the other stuff which sort of tracks what are the local variables, the name of the local variables, and the value stored in these local variables corresponding to each and every function, right? But when you remove the debugging information, all this information is lost, and you cannot try to look at the source code. So if I sort of do this command called list, right? So previously, if you remember, when I did list, it sort of lists the source code. But when I do this list command again, right, it doesn't have this symbol table or the source code to assembly code mapping and all those stuff, right? So all that information is sort of lost, and GDB cannot help you in recovering what the local variable names are and all those things. But still, what you can do is you can inspect what your local variables are. So for example, I can specify my EBP, my ESP, right? And I can look at the dump of the ESP. So somewhere on your stack memory only your local variable should be present, right? So for example, if you look at right, so if you look at for example, if I change this value a equal to 6, okay, and I just recompile the code, and I okay, so I run the program. I inserted a breakpoint at the same location, and now I just look at the values of the stack content starting from that stack pointer ESP. So if you notice over here, at the address FC triple F FC0 F4, okay, at F4 you have this value 00006, and at address uh, C0F8 you have this address you have this value 1, and if FC you have this value 2. So if you notice over here, the variables A, B and C, right, as this local variables which are stored on the stack region, they have this value 6, 1 and 2. So if you notice, right, uh, the same values they are present on the local memory, the stack. So you can sort of try to correlate, right? So these are the variables A, B and C which are being stored on the stack location in the stack memory. Okay. And so these are like sort of the general commands in GDB, and another useful command is something called as layout ASM. So for example, if I want to look at instead of looking at the disassembly file separately, right, what I can do is if I'm like stepping through every single instruction, I can use this command called layout ASM, and this layout ASM is basically it splits your screen into two windows. The top window is for showing your assembly code, whatever is being executing currently, it shows that pointer, and the bottom window you can interact with your GDB tool. So if I single step, if you notice, it highlights which instruction is currently going to execute, right? So if I again single step, it sort of keeps on highlighting which instruction is going to execute, right? And the other layout is layout registers. So what I can do is if I just do so TUI off, so TUI so what I can do is I can okay, so the same instruction 0x, I insert a breakpoint and I just do the run command. So what I can do is I can so if I just do layout registers, it's mentions it's like this. So it gets split into three windows. The top window is for the register contents, and the second window is for the assembly code, whatever is being executed, right? So for example, I'm doing a move instruction. If I so the value of EAX is 0x18. So if I single step through the instruction, you notice that my EIP register is changed. That's what being highlighted, and also my EAX register is being updated with this value 80E6C8C after I executed this instruction. So the same way, if I single step through the instruction, it sort of highlights what registers are being changed and also which instruction is being executed. Right. And the other important thing that you should do whenever you're using this layout assembly and those stuff, right, is should set the disassembly flavor to Intel. So what I mean by disassembly flavor is, um, so currently if you notice, the way that your disassembly is usually present, right? So for example, if you notice, if you look at this specific instruction 49DCA, right, you have this instruction move EAX comma something, some value, right? So the meaning is it moves this constant value 0x80E6C88 into this EAX register. So this type of representation is usually called as the Intel representation, right? The Intel format of disassembly instructions. But let's look at an alternate one, what is called as the ATT. So if I, so if you notice when I got the disassemble file using object temp, I specified over here -m Intel. But instead of specifying -m Intel, if I just do it in normal way without specifying the flag, let's see what happens. So at same address 49DCA, I get this instruction. If you notice over here, the register has been changed. The instruction notation, right? So previously it was move EAX, comma this specific value. It was like this, but now without the Intel flavored disassembly syntax, the operands have been changed. So this is known as the AT&T ATT representation. Usually, in most of the books or whatever guides or like sort of online resources you go through whenever you are looking at GDB or some binary exploitation or something, usually they'll be following the Intel disassembly flavor because it's more sort of aligns with the way you code in your C code, right? Because say if I want to um, say if I want to assign some variable, for example a equal to 5, right? The LHS represents the location where you want to store the variable and the RHS represents the value what you want to store. So in the same way, move EAX comma this value, it specifically means LHS is the location where I want to store, which is the register EAX, and RHS represents the value what you want to store. But in this AT&T format, it sort of gets confusing, right? You should like sort of read it in the opposite way. So this will be sort of confusing, and also they have this notation of every register gets prefixed by this percentage sign, and every constant gets prefixed by this dollar sign and all that stuff. But this sort of like confusing and all that stuff. So whenever you use this layout assembly mode, you should set the disassembly flavor to Intel. Otherwise, what happens is if you set it to, if I just normally use AT&T, so what happens is it sort of, it does not use this Intel flavor. So for that only I should explicitly set the disassembly flavor to Intel. So if I just do SI, yeah, it has changed. So this is what it shows. These are the commands, right, in GDB, and based on whether your um, the debugging information is present or not, the amount of information, the commands, the usability of these commands varies. So, for example, this info locals and those commands will sort of not work when your debugging information is not present. When it's present, it will come in handy. But usually, in your assignments and all those stuff, the debugging flag mostly won't be enabled. You can check whether it's enabled or not by looking at the file output. So you can just do file space executable name, and you can see whether the debugging information is enabled or not. You will have this keyword with debug underscore info like that. So and yeah, and another command which so if you want to execute from this layout mode, you use this command called TUI disable, right? And if I want to enable again, I can sort of use this TUI enable. Okay. And the other command that is sort of interesting is called as the watch command. So, so for example, I know. So if for example, let us look at the source code, and so I have this GLB um, character, right, a global variable. And what I can do is first I'll find out the address of this global variable. So p/x ampersand GLB. So this is the address of the global variable, okay, and this is the address, and this address won't usually change, okay. So that's like since we have statically linked, the address of these global variables will sort of not change mostly. There are other aspects also, but for now just assume, right, the global variables address won't change, okay. If it's say present at this specific address in different invocations of the same program, multiple times I run it, how much ever times, it will be staying at that same location. The address location is sort of fixed, okay. And what I can do is I can just continue execution. It exits. So now if I do some SI or something, the program is not being. So what I can do is instead of say I want to insert breakpoints, but I'm not sure where to insert the breakpoints, but I know for a fact that I want to insert a breakpoint such that I want to inspect the program contents wherever this value of GLB gets um, changed, right? So what I can do is I can use this command called watch command. So watch specified by the address, and the watch command is sort of pretty powerful. There is one variant of the watch command, okay. So watch specified by star address, okay. So I do this watch point, and so basically what happens is um, what it does is in x86 hardware, as part of the processor itself, some features are there which are called as hardware watch points. So when I specify watch followed by some specific address, what it will do is whenever I am trying to write to some address location or even read from a location, what happens is whenever I try to access that address location, it will pause execution of that program and notify you that this specific address location, whatever you have instructed the x86 hardware to watch closely or monitor, right, that is being accessed, and stops execution then and there and notifies you. So for example, if I start running the program, so if I just disable breakpoints, right, so info breakpoint. Okay, so the hardware watch point is also a breakpoint actually. So what I do, I enable breakpoint 2. Okay, so the hardware watch point alone is enabled, whereas the other breakpoints are not. So what I do now is I just execute this command run. So now if you notice, it is sort of stopped at some location which is 8049 DD3, and if you notice, it mentions old value 0, new value 22, and the watch point is this specific address. So this is specifically the global um, variable that is being written to. So this specific instruction over here, right, GLB equal to 22, this is the specific instruction where it stops, pauses execution, because I'm writing to that specific address whatever I specified, and the hardware notices that address has been changed, the value at that address is being changed, and it pauses execution. And say if at some other location also I access GLB, it will again pause execution. Okay, so this is the so for example, I do GLB plus plus at this location. Okay, so again it pauses execution and mentions the old value and the new value. So the I just increment by 1, right? So it increments by 1 and it specifies the new value. So if I just do continue, it exits because there are no other breakpoints and that specific address location is not being returned to or read, right? So it just exits the process. So this watch command is pretty powerful. I'd encourage you to look at the GDB manual or online resources. Like I'll be sharing a link, so it will contain all these different commands and all those sort of stuff related to GDB, and it will come in handy. So this is the whole idea of GDB and what you will be using it, right? And for example, when you want to say when you are just given a binary, add out binary, and if you want to find out any exploit or something, so what will you be doing? How do you start is first you will try to look at the disassembly. You will try to understand what the program does usually. You won't have access to the source code. So what you will do is you will first execute the program in a normal way. You will try giving different inputs, understand the logic. And then afterwards you will try to look at each instruction. You will step through each instruction and see what each instruction is being doing, and you will try to get as much as information possible. And for that GDB will come in handful. Say for example you want to inspect the stack contents, you want to inspect some memory contents and all those stuff, you can use GDB and try to execute a binary within the GDB. Okay, so this is the basic commands that will be useful when you execute when you start using GDB. And okay, so that's the end of this lecture, right? So we looked at the basic commands in the GDB and all those stuff. And before wrapping up this lecture, I'll be releasing the assignment. I'll be showing the assignment also. So ISS. Okay, so I have updated the assignments. So you have assignment 1, which is due on 9th December. So it's a pretty normal assignment only. So uh, there will be 3 questions, and for each question you will be given corresponding binary file also. So for question 1 it's prob underscore 1, for question 2 it's prob underscore 2, and for question 3 it has 4 binary files, 3A, 3B, 3C and 3D. Okay, and so read through each question and try to identify. So some questions have like 3 subparts like that. The questions are pretty simple. You just have to look at the disassembly. So I've given the executable, the ELF binary files. You should look at the disassembly, or you can run it through GDB also, and you should try to answer the question. So for example, in one question I'd have asked the number of parameters passed to the add1 function. So you should identify where the add1 function is. You should identify which function is calling add1. Try to find the number of parameters being passed. So you can either use GDB or you can just statically look at the source code at the disassembly and try to find out number of parameters being passed. Okay, and you should find out the return value. So to find the return value, you should know the ABI, right? So which register is being populated for that return value. So all this stuff will be, you should be using, and you should try to answer these questions. And I have given a form through which you should submit all your um, so it is a team-based assignment, right? So one submission per team, and you should just name it as assignment1.pdf and submit it in this Google form. upload the PDF file. So it can either be a handwritten or it can be like even typed out document. You can refer to any online sources, anything, right? And try to answer these questions. So this is assignment 1, and in tomorrow's lecture we will be starting with our first software exploit, that is Stack Overflows. Okay, so thank you everyone. If you have any queries or anything, do post it on Discord channel. Thank you.